This video is about Chapter 13, and in this video we'll talk about experiments and observational studies. By the end of this video, you should be able to describe the differences between observational studies and experiments. You should also be able to explain 4 principles of a well-designed experiment. Actually, there are 5 that we're talking about in this video. And you should also be able to define and give examples of confounding variables. First, an observational study. Observational studies are studies where the researchers do not influence the subjects. They simply observe them. Okay? So one example is a survey that asks students whether or not they eat breakfast on a regular basis and their GPA. And they're looking to see if there's some kind of an association between whether or not students normally eat breakfast and their GPA. Okay? Observational studies are usually retrospective, meaning they're talking about data from the past. So in the past, have you eaten breakfast and what's your GPA? Okay? But sometimes observational studies are prospective, meaning it's going into the future. Okay? So from here on out, we can take a group of students and we can see going into the future if they eat breakfast and what their GPAs are going to be in the future. Okay, retrospective are about the past, past, prospective into the future. Okay, now I will tell you that prospective studies, as far as I know, are most commonly done in the medical field. Okay, they may take a group of children and follow them over the course of their lives and see, what things may have influenced certain, medical treatments or medical conditions. Okay, or they may take a group of adults and follow them over a number of years and see which of them have heart attacks or which of them get cancer. Okay, prospective studies go into the future and look at what's going to happen in the future, but most are retrospective. Okay, down here at the bottom, there's a note in red. You can't conclude causation from an observational study. This is huge, at least to me. Okay, for example, even if you find in the study about breakfast and GPA that most students who eat breakfast do significantly better, far better than students who don't eat breakfast, you cannot conclude that eating breakfast alone will cause students to get better grades. There may be other factors that are influencing grades than just whether or not they eat breakfast. Okay? Perhaps the students who get up earlier to eat breakfast are the kind of student that just naturally does better at school. Okay? Or there could be other factors that are influencing both whether or not students eat breakfast and GPA. For example, maybe high parent involvement could influence both of those things. Okay, the important thing is you cannot conclude that one will cause the other from an observational study. That's different from an experiment. In experiments are studies where researchers impose a treatment. They do something to the subjects and then research how that treatment changes some response variable. Okay, so for example, we could do an experiment with breakfast and GPAs. Okay, here's an example. You could randomly divide a group of students into 2 groups using randomization. Okay, so randomly into 2 groups, give one breakfast every day for 6 weeks. And then you compare that group with the other group at the end of 6 weeks and see if there's a difference in GPAs between the 2 groups, okay, or a difference from before and after the experiment. Okay, in a well-designed experiment, and I'll talk about the 4 principles of a well-designed experiment in a minute. In a well-designed experiment, you can conclude that one causes the other because theoretically you've limited all other variables except the one that you're imposing. Okay, so from an experiment you can conclude causation, that eating breakfast results in better grades. Okay, now there are 4 principles of a well-designed experiment that you should follow. They are, first, control group to compare. Number 2, randomization to reduce bias. Number 3, replication to reduce individual differences. And 4, block, when your population comes from different groups. So the first is a control group to compare. In a well-designed experiment, there must be more than one group receiving a treatment, so we have something to compare to. Okay? Almost always, we don't impose any treatment to one group, so we can use this group to compare with the other group or groups. This group that we don't do anything with is called the control group. It's the group that we're doing nothing with, so we can compare that with our other treatment groups. In medical research, sometimes patients are given a placebo, which is a pill with no medicine. Okay, and this group becomes the control group. They found that if you do simply nothing to patients, that there's often no change or a decrease. Okay, but if you do something, if you give them a pill that has no medicine, sometimes they think they will get better, and so they just will naturally get better just by psychological reasons. That's been thoroughly studied. Okay, so there should be some groups that you can compare with other groups in an experiment. Number 2, randomization to reduce bias. Randomly assigning subjects to treatments will reduce bias. Okay, so for example, in our breakfast and GPA study, if a certain kind of student is more likely to select the breakfast or no breakfast treatment, then this would create bias in our study. I'm pretty sure that every student, if they could select, would select the breakfast group. But maybe this isn't the best example to talk about randomization, but let's kind of just imagine that there is a group of students that already eats breakfast at home, and therefore when they come to school they don't need breakfast given to them. Okay, let's say that group is fundamentally different from the group that needs breakfast because they didn't get breakfast before coming to school. Okay, so that self-selection could create some bias, and we would lose our ability to say that eating breakfast causes higher GPAs, if that's what happened in the study. Third, replication to reduce individual differences. Okay, there are 2 ways that replication is important. Okay, the first has to do with, in the study, there should be enough subjects in each treatment group that the group's summary data, like the mean or the median of the data, isn't influenced by 1 or 2 individuals. Okay, you have enough people there, that could be 10 or 20 or 30. You will see a general trend in this class is the more data we have, the better. Okay, but there should be enough people in your treatment groups that you can look at some summary data that's not influenced by 1 or 2 outliers. Okay, second place that replication is important. The experiment should be repeated with different subjects in different locations or in different settings. Okay, for example, the study about breakfast and GPA may have a different result if conducted at a different school. Okay, so if you repeat the experiment in a different place and with a different group of students, that may give you a different result. Okay, fourth principle that should be followed if you can. Sometimes your population comes from different subgroups that may affect your study. Okay, in this case, you should consider a randomized block design. Okay, this may look a little complicated down here, but here's an example of a block design. Let's say we think that honor roll students compared with non-honor roll students may respond differently in this experiment. Okay, so we decided to block based on honor roll. Okay, let's say from our 20 students we happen to have 8 that are honor roll students and 12 that are non-honor roll students. Okay, we randomly assign 4 of the honor roll students to group 1 who gets breakfast and 4 students to group 2 who don't get breakfast. Okay, and then from our 12 non-honor roll students we randomly choose 6 of them to be in group 3 to receive breakfast and 6 of them to be in group 4 with no breakfast. Okay, and then we compare the GPAs within each group of honor roll, non-honor roll. Okay, so what this does is it reduces the effect that honor roll and non-honor roll could have on our study, because we're kind of taking into effect making sure that we have the same number of honor roll and non-honor roll students in each group breakfast and no breakfast. Okay, a similar thing could have been done with gender. Okay, if you think that gender would affect this study, then you could block by gender, having, maybe there's, 10 male students and 10 female students. And then you randomly assign, 5 males into the breakfast group and 5 females into the breakfast group, and the other 5 males and 5 females could go into the no breakfast group. Okay, so you could block based on gender or any other variable that you think would affect your study. Okay, fifth is not part of the 4 principles, but it's one that is possible to use, and you probably should use if you can. Okay, and the idea is blinding. One possible component in designing an experiment is blinding, and it can happen in 2 places. First, the subjects or participants don't know which treatment they are receiving. Okay, this happens when treatments are receiving a placebo. They don't know if they're receiving the placebo or not. Now, let me just back up. That you would only get a placebo from a hospital if you knew that you were involved in an experiment. Okay, they won't just start randomly giving you a placebo instead of your medication to see what happens with you. Okay, that only happens in medical research in an experiment. They will tell you that you're part of an experiment. Okay, so don't be worried that you will be taking a placebo instead of your medication when you get it from a doctor. That only happens in medical research, and you know that you're in an experiment. Okay, so if you don't know which treatment you're receiving, that's blinding. Okay, the second place that blinding can happen is those that are assessing the subjects or participants. That those assessing them don't know which treatment they are receiving. Okay, if those assessing knew that this was in this group and this person was in that group, that may subconsciously or may affect their assessment of the individuals. Okay, experiments with one of these, either one, is called a single blind experiment. And experiments with both of these are called a double blind experiment. So they don't know which treatment they're in. Okay, the last topic in this chapter is about confounding variables. Okay, when the levels of one factor are associated with levels of another factor, we say that these 2 factors are confounded. Okay, because of the confounding, we can't tell whether any effect we see was caused by our factor or by the confounding variable, or even by both working together. Okay, so for example, with our breakfast experiment, if we didn't use a block design, and we're pretty sure that the variable of honor roll versus non-honor roll may have been a then that variable may have been a confounding variable. Okay, because we don't know how that variable would have affected our study. There could have been other factors like gender, weather, if it's, good weather outside, or class schedule. If this group happens to have a bunch of really hard teachers or really hard classes, that could affect the study. Okay, so confounding variables are when other factors are in our experiment than the one that we are studying, or the ones that we are studying. Okay, we do our best to limit the effects of confounding variables using a well-designed experiment. So this video was about experiments and observational studies. You should be able to describe the differences between an observational study and an experiment. You should be able to explain the 4 principles of a well-designed experiment and talk about blinding as well. It's not one of the 4. And you should also be able to define and give examples of confounding variables. Thank you so much for watching.